Okay, so the next chapter that we have to do is reaction kinetics. Reaction kinetics. Or in simple words, it's a chapter that's related to the rate of a reaction or the speed of a reaction. All right. And how can you affect that speed? What factors affect that speed of reaction? How a reaction basically takes place. All right. What are the things that happen during a reaction that you have to study? Then you have to know what factors are there which affect this rate of reaction. So if you want to, for example, increase the speed of your reaction, how do you do that? What are the factors that can control the speed of a reaction? So basically, in reaction kinetics, the first thing that you need to understand is collision theory. Collision theory. Now, collision theory says whenever you want to react two reactants together, what's the first thing that must happen over here? That first thing is
Their
that
bonds must be broken.
these two reactants must come in contact with each other, or they must collide with each other, right? Without
Yep.
coming in contact with each other, there's no possibility for a reaction, right? So the first postulate for collision theory is that reactants must collide with each other, with each other. So they may react. So they may react. Now, this is very important. Why do I say they may react? Because it's not only dependent upon colliding with each other that you'll make product. All right. So the formation of product or the reaction of the reactants is not just dependent on the collision. There's other things also. Now, the second point is that when these two reactants collide with each other, they should have enough energy to form product. Or in other words, by forming product, I mean breaking old bonds, breaking old bonds and forming new bonds. Because in the product, you'll have different bonds compared to the reactants. You'll have new bonds over there. All right. So the second postulate would be they must collide with enough energy, enough energy in order to form product. All right. But again, they may, if they have enough energy, they may or may not still react with each other. Because there's a third factor involved over here. And that's the third postulate, that their orientation must be correct. They must collide with the correct orientation. I'll explain this with an example. They must collide with the suitable, we can say with the correct or the suitable orientation. I'll explain this with an example because this A and B molecules, that not very easy to understand that collision orientation from there. So I'll give you an example. For example, if you have a molecule of an alkene, that is ethene, for example, you've not studied this yet, but still just go with it. So ethene, what's the behavior of ethene? Ethene has a lot of electrons to give. All right, there's a lot of electronic cloud over here, or electronic density, a lot of negative charge on ethene that it wants to give to someone. All right, because it has a double bond, it has a pi bond. So these pi electrons are over here, and ethene wants to get rid of these electrons. All right, and what are you reacting ethene with? You're reacting with HCl. Now, HCl is a polar compound in which hydrogen is less electronegative, so it has a slight positive charge, and chlorine being more electronegative, it has a slight negative charge. Now these two molecules come into contact with each other. All right. So I'm going to draw it like this just to make it easier for me. These are the hydrogens, and this is the double bond of ethene. All right. And for HCl, I'm going to draw it like this. All right. The larger atom is chlorine and the smaller atom is hydrogen, and same goes over here. Now, if they want to react with each other, first of all, they must collide with each other, right? That's the first postulate for the collision theory, that in order for a reaction to occur, the reactants must collide with each other. So the first thing is that these two things need to collide with each other, right? The second thing is that both of these molecules must have enough energy so that when they collide, they're able to break the previous bonds and form the new bonds. Is that clear?
Yep.
All right. So the second thing is that they must have enough energy so that when they collide with each other, they're able to break the previous bonds and form the new bond. That means they're able to form a product out of this collision. All right. So, but this is still not enough. Why? Because there's a third point. They need to be in the correct orientation in order to react. And now I'll explain that point over here in detail. Now, in order to form product, how should they collide? Let's see that. Now, we do know that when ethene wants to react, it wants to get rid of these electrons over here, right? The pi electrons, the pi electronic cloud. It has a lot of electronic density that it wants to give to some other molecule in order to form product. Now, who in the HCl molecule wants those electrons? Is it Cl negative, which is already quite negatively charged, or hydrogen, which is slightly positively charged? It has low electron density, or it is electron deficient. Who wants these electrons from ethene?
The one who's electron deficient?
Yep. So hydrogen wants these electrons from ethene, right?
Yep.
So whenever these two molecules collide with each other, hydrogen wants to be facing these electrons over here, right? Hydrogen wants, the correct orientation would be that hydrogen is facing these pi electrons so that it can directly go onto those pi electrons and then break its previous bond, form the new bond over there, right? So we want this part of the molecule to be colliding with these electrons over here, right? So right now, if I look at the orientation, is this the correct orientation? Is this the correct orientation for the collision? It's not. Although you have enough energy, although you're colliding with each other, but you'll bounce back. You won't be making any product. All right. Now let me see if I can rotate this. Um, let's do this. Yeah. So if I collide like this, is this going to result in a product? Yep. Is this going to result in a product? So I want this part to be facing this. Now, do you think
Yep.
this collision is going to result in a product?
Yes, I think
Nope.
so.
Nope. Not like this. Not like this. Because it's colliding with these hydrogen atoms over here. Right? The hydrogen atoms from ethene, that's what the hydrogen and the chlorine are colliding with over here. No, this is
Okay.
not the correct orientation either. Is this the correct orientation?
No, it's still
This is
colliding.
not the correct orientation either. Right?
Yep.
All right. So is this the correct orientation? To be colliding like this?
No.
Is this the correct orientation? Like this?
Yes.
No. Again, what do I want? I want this hydrogen to be directly going towards the pi bond, right? So I'll show you the correct orientation now. Your molecule should be heading towards the pi bond like this. This
Okay.
would be the correct orientation for colliding, right? Because now you have enough energy, You're colliding with the molecule and you're colliding with exactly at that point where the reaction is going to occur. This would be the correct orientation over here. All right. When the hydrogen from your HCl molecule is directly colliding with the pi electrons over here. This would be the correct orientation. Apart from this, any other orientation, if you collide like this, if you collide like this, with chlorine facing towards the pi bonds, if you collide like this, any other orientation would not be correct. All right. So let's draw the different types of orientations which are possible over here. So this is one orientation. This is not the correct orientation. All right. Then the second one could be like this. Let me just redraw this. Um, let's duplicate this and rotate. The second one could be like this. Chlorine facing towards the pi bond. Is this going to result in a chemical reaction over here?
No, it should be the
No,
other side, right?
right? Again, this is also not the correct orientation. So we'll cross this. And I'm not going to draw all of them, but let's do some of them. What about this orientation over here? Are they going to react like this?
No.
This is also not the correct orientation, right? So in this collision, they're going to collide with each other and then bounce back. That means no previous bonds were broken, no new bonds were formed. They just bounce back and remain in their own states, right? They remained as their reactant states. What's the correct orientation over here? That is when the alkene or the pi bond for the alkene is directly attacked by, sorry, it directly attacks what? It directly attacks the hydrogen over here. This would be the correct orientation. Now, this will result in a product. How? Both of them will be breaking their previous bond and then linking up together to form a new bond. All right. So this is the correct orientation. So collision theory says three things. Let's just go over that again. So first thing, reactants must collide. If they want to react with each other, they must collide. And with this collision, they may or may not react. Why? Because then the collision must have enough energy to break the previous bonds and to form the new bonds, right? To form the product. And then, even if they have enough energy, they must collide with the correct orientation, right?
Yep.
So, if they have all three things, point one, pass. Why? Because they're colliding with each other. Point number two, we're good in that also. Why? Because they have enough energy to collide with each other and they have enough energy that if they collide correctly, they can break their previous bonds and then form new bonds. All right. And then point three, they must collide with correct orientation. This is the best orientation they can collide in. Any orientation from this or apart from this, that won't result in any product, no matter if you have enough energy or if you're colliding. They'll bounce back. All right. So there's two types of collisions. Keeping these 3 points in mind, there's two types of collisions. The first type, we call it as effective collision. And the second type is ineffective collision. Now, an effective collision says, or effective collisions happen when reactants collide with enough energy and orientation correct orientation so that they result in the formation of the product. Or in our own words, effective collision is collision which forms product. That means in this collision, the reaction actually takes place. What about ineffective collisions? Ineffective collision is when reactants collide with either of these conditions are not true. So with insufficient energy, or incorrect orientation resulting in bouncing back and not making any product. So here the reaction does not take place. So no product forms in ineffective collisions. So what do you understand from this? Now, when a reaction is taking place or when you mix two reactants together, do you think that a lot of collisions are happening?
Yep.
Yes, a lot of collisions are happening because a lot of molecules are colliding, right? There's a large number of molecules present inside the reaction mixture, which are constantly colliding with each other. So there's not a problem with the number of collisions that are going to happen, right? The problem is that if those collisions are effective or ineffective, which ones do we want to happen?
Effective
We
collisions.
want effective collisions. We want the majority of the collisions to be effective so that product is formed and the reactants don't bounce back from each other, right?
Yep.
So now let's link this together. So let's say when a reaction takes place, reactant molecules undergo, reactant molecules collide with each other, and a large number of collisions take place. Now, out of these large number of collisions, if the proportion of effective collisions is greater than the proportion of ineffective collisions, what do you think is going to happen?
If effective is more than ineffective, then
Yep.
it's going to
It's
work,
going to
right? The
form
products
more
will
product,
occur.
right?
Yep.
It's going to form more product and it is going to form product more quickly, right? So that's the first point that we're going to write. Now, if the proportion of effective collisions is larger than ineffective collisions, in other words, or in lay language, you can also call this fruitful and unfruitful collisions, right? Fruitful being the effective collision and unfruitful being the ineffective collision. So uh, if the proportion of effective collisions is larger than ineffective, then more product is formed per unit time. So for example, if in a minute, you just look at a duration of a minute and you've started a reaction and you record it for a minute and the reaction ends, then you see how much product you've formed. If you formed a lot of product in that minute, that means the effective collisions were very large compared to ineffective collisions, right? And in that
Yep.
same minute, if you do not get a lot of product, what does that mean? That in that reaction or under those conditions, the effective collisions were very less compared to ineffective collisions. That's why not a lot of product was formed. Is that clear?
Yep.
So if I say if the proportions of ineffective collisions becomes larger than effective collisions, effective collisions, then less product is formed in the same amount of time or per unit time. Is this clear?
Yep.
Now, I want you to link one more thing. If more product is formed per unit time, so let's take 1 minute. So if more product is formed in 1 minute, and in the other case, less product is formed in 1 minute, formed per unit time, where is the reaction faster?
More product is formed per unit time.
The reaction is faster where more product is being formed in the same amount of time, right? So in both of them, I've taken 1 minute. I conducted a reaction for 1 minute. It was the
Yep.
same reaction, but I changed some conditions. So in one case, I'm getting more product in the same amount of time, and the other case, I'm getting less product in the same amount of time. Where was the reaction faster?
It's the same amount of time.
Yeah. Where was the reaction faster? Where was more product being formed in the same time?
The first one, more
Yeah.
product is formed per unit time.
Yep. The more amount of product is being formed in the same time. That means the reaction proceeds faster. All right.
Yep.
So more product is formed per unit time. Reaction is fast. Or if less product is formed per unit time, reaction is what? Reaction is slow. Right? Now let's think
Yep.
about one more thing. That just skipped my mind, man. More products formed per unit time. Reaction is faster. Yeah. The thing is that how will more product be formed and how will less product be formed? What is going to form the product?
Effective collisions.
Yeah. So can I use alternate phrasing for this? Can I say more reactants are consumed per unit time in a reaction that is fast,
Yep.
right? Because if a reaction is fast, that means more reactants are being consumed in order to produce more product in the same amount of time, right? So if in a
Yep.
reaction, more reactants are consumed per unit time, that still means the reaction is fast, right? Because those reactants will be converting into product, right? And if less reactants are reacting in order to form product per unit time, less reactants are consumed per unit time. What does that mean? You'll get less product per unit time. And that means less product means reaction rate is slow. Is that correct? Are we clear?
Yep.
So now let's move on to rate of reaction. Now this is the most important thing for which we've done all this previous information. Now let's start with what is rate. What is rate? Mathematically, it is the change of any quantity with respect to what? Time, right? That's rate. Change of any quantity with respect to time, that would give you rate, right? For example, if you're talking about the rate of distance that you cover per unit time, what is that known as, by the way? That's known as speed. What is speed? Speed is the change of distance per unit time, right? Or rate of change of distance per unit time. That's also speed. So rate is any quantity with respect to time. So we can define rate as the change in any quantity with respect to what? Time, right? Now in chemistry, what is rate or rate of a reaction? Now let's define rate of reaction. What is rate of reaction? It is basically the change in concentration of your reactant or your product. So it can be measured with either of them. Either you see how much reactants are being consumed per unit time, or how much product is being formed per unit time. All right. Both of them will convey the same rate for the reaction. All right. Because the reactant that is being consumed is being converted into the product simultaneously. Right. So change in concentration of reactant or product per unit time. That's known as our rate of reaction. So I'll define it. So it is the change in concentration of reactant or product per unit time. All right. Now I'll make it easier for you. We can either say that rate of reaction, if you talk about the reactants, is the amount of reactant consumed per unit time. Or you could also say that rate of reaction is the amount of product formed per unit time. Is that clear? So either of them, they both convey the same rate because the reactants that are reacting are being converted into the product. Is that
Yep.
correct? Right? So you can use either of them to calculate the rate of reaction. All right. So rate has two equations, or you can use two methods to calculate rate. It's either the change in concentration of reactant per unit time, or you could also say that rate of reaction could be change in concentration of the product formed per unit time. All right. And over here
Yep.
by per unit time, I mean per minute, per second, any times, any unit for time that you want to use. All right. So it would be per minute, per second, per hour, whatever unit that is suitable for the reaction. If the reaction is very fast, then it's better to calculate the change of concentration per second. If the reaction is like medium, it's better to calculate the change in concentration per minute. If it's very slow, it's better to calculate it in hours. What's the change in concentration per hour? All of them would be conveying what? They'll be conveying the rate of reaction, the speed of reaction. This much reactant is consumed in this much time, right? So basically, if I say the rate of reaction is 0.1 mole per dm cube per second, what does that mean? It can either mean that this much reactant is being consumed per unit time or per second, or it could either mean that this much product is being formed per second in the same reaction. All right. And so now if I know the concentration of reactant being consumed per second, can I like now start thinking about if the reaction is or the speed of the reaction? how fast the reaction is going to proceed, right? Can I start relating it with the speed of the reaction,
Yep.
right? Because I know that per second, this amount of reactant is reacting, or per second, this much product is being formed. So now I can really start thinking about the speed of the reaction. That means the rate of the reaction, how fast the reaction is going to go, right? So if I draw another example over here and I say that 1 mole per dm cube per second is the rate. Now, if 1 mole per dm cube of the reactant is being consumed in every second, is this reaction faster or this reaction is faster?
1 mole per dm
Yeah,
cubed.
where more reactant is being consumed per second, because in that reaction, more product is being formed per second, right? So this would be a
Yep.
faster reaction because more product is being formed or more reactant is being consumed, right? So where is the rate of reaction faster?
And the one that has more.
Yep, and the one that has 1 mole, right? Because over there, more product is being formed in that same second in which in the previous example, the product formed is very little compared to this one, right? So over here,
Yep.
less amount of product in that same second, and over here, more amount of product in that same second. What does that mean? That in the previous example, in 1 second, less amount of reactant is being reacted or converted into product. And over here, more reactant in the same second is converting into product. So where is the reaction faster? Over here. So this would be a faster reaction. This would be a slower reaction. Are we clear? So what is
Yep.
rate of reaction? It is basically the change in concentration of the reactant or the product per unit time. All right. Or if you stick to reactants, then it is the amount of reactant being consumed per unit time. If you stick to products, it is the amount of product being formed per unit time. Are we clear?
Yep.
So do you remember the equation for rate? This is rate of reaction. I'll write ROR. This is rate of reaction and it's equal to the change in concentration of reactant per unit time or the change in concentration of product per unit time. Either one of those. All right. Now,
Okay.
let's link this. Now, let's say that this was the same reaction. A was going into B. This is the reactant and this is the product. Now, in the first case, this was the rate of reaction. All right. You were forming 0.1 mole per dm cube of product per second, or 0.1 mole per dm cube of reactant was reacting per second. The reaction rate of reaction was slow. But how do I make this same reaction be faster so that more product is formed or more reactants are consumed per unit time? So there's ways to make this reaction faster, all right? And those are the factors that affect the rate of reaction.